Okay, so in this example, we're going to look at a specific function and ask the question, is the function surjective? Is it injective? And then for each case, we're going to answer with yes or no, and then we're going to prove it. All right, so the function is this. It's a function that maps from R cross R. This is the Cartesian product. So this would be like basically ordered pairs. And then it maps to R. So the function is this. H of xy equals x plus y. So essentially, it's like our input is an ordered pair, which is two real numbers. And we get our output by just adding those two real numbers together. Okay, if anybody in the class is in or has taken multivariable calculus, this is the type of function you work with a lot in multivariable. It's a function of two variables where the inputs are both real numbers and then the output is also a real number. This is the sort of function that you can map that sort of creates like a surface map in the XYZ three-dimensional space. So anyway, you don't need to have taken multivariable calculus to understand what I'm doing here. Okay, I just wanted to make that connection. So first of all, the question is this surjective? Oh, actually, before I do any of that, let me just do a couple of examples here. If I do like h of 5, -2, this is going to be like 5 plus -2, so this is equal to 3. Right? If I do h of like 2.7, comma 0.1, this is going to be 2.7 plus 0.1, so this is 2.8. Okay, so I just wanted to do a couple of examples so you get the idea here. Okay, any real number inputs are fine, and the output is obtained by adding the two inputs together. So now, let's think. Is this going to be surjective? All right, the question surjective is it going to map onto the entire codomain, right? So is it possible by adding two real numbers together to get any real number? Well, sure it is. Yeah, right? Anytime you can get any real number, right? If you pick the right two real numbers to add together, you can get anything. Yeah, we should be able to prove that. I think the answer here is yes. But how do we prove it? Well, let's go over that. What we need to do here is actually start with like an arbitrary element of the codomain and then somehow prove that that element has a pre-image. Prove that that element is in the range because we want to find some input which will map to that specific element. Now, if that element was arbitrary, then we'll then have shown that we could do it with any element, and therefore it's true of all elements. That's called the universal generalization. So we're going to start with an arbitrary element. I'm going to call it z, right? We can't use a specific number. Like when we say arbitrary, it doesn't mean like pick any random number and use it. I'm not saying we're going to like pick 5. No, an arbitrary element means just pick a variable, say that it's in that codomain, but don't specify what it is. It could be anything, right? So let z be in the set of real numbers. That's our codomain. Now what I want to do is find some input which is going to map to z. Well, z is a real number, right? So our input needs to be two real numbers that when added together give you z. Well, z could be one of them, right? Because it's real. And for the other one, I might as well just take 0. So this isn't the only thing I could do, but the simplest thing I can do here is just consider the number, or consider the element z comma 0. That is an element of R cross R, right? Because z is a real number and 0 is a real number. And in particular, that is the one I want to consider because if I plug it into my function, h of z comma 0, that's going to be z plus 0, which is just z, right? Hey. So that was nice and easy because I just showed that there's guaranteed to be an input that is going to map to this output, right? So what I've shown is that therefore z is in the range of this function. Z is in the range. Okay, now since z was arbitrary, I want to make a point of that. Since z was arbitrary, that means that all real numbers, I don't know why I wrote 2 L's, all real numbers are in the range. Okay, therefore, H must be surjective. Okay, There we go. So that proves that it's surjective. All right, what we did was we said, let's take a real number, prove that that real number is in the range, and then say, well, since it was an arbitrary real number, it could have been any real number, therefore all real numbers are in the range, right? Remember, that's universal generalization. Therefore, if all real numbers are in the range, well, the range is the entire set of real numbers, which is the codomain. So there we go. Now, I want to make a note here. Okay, just kind of an aside, a note, that what we proved here was, strictly speaking, we just proved that the codomain, which is the set of real numbers, is a subset of the range. Okay, because we proved that any element of the codomain is therefore must be an element of the range. That is one directional. That proving that the codomain is a subset of the range. But range is a subset of the codomain, basically by definition. Okay, the range is always a subset of the codomain. So if you prove that two sets are subsets of each other, that proves that they're equal. Remember that from section 2.1, right? If you prove that two sets are subsets of each other, then it proves that they're equal, the same set, right? And we don't need to prove the second part here. We don't need to prove that range is a subset of the codomain because that's just a given. All we need to prove is that anything in the codomain is in the range, and then we'll get what we need for surjectivity. So I just wanted to make that note. That I did not include that in my proof, but this is kind of what's going on under the hood. This supports the conclusion here. I didn't actually appeal to it in my actual in the text of my proof, but this is, strictly speaking, what is going on. So now we've dealt with the surjective question. Now let's ask the injective question. Is this function injective? In other words, is it one-to-one? So remember, injective would mean that that basically for any input, for any two inputs that are different from one another, the outputs are guaranteed to be different from one another. So to explore this question, you could ask something like, is it possible to get the same output from two different inputs? Well, in this situation, sure it is. I mean, you're just adding two numbers together, right? Adding the two inputs together. So couldn't you get the same answer by adding two different numbers together? Like you could do, like, let's just think of an example real quick. We could just do, we're going to do, hang on, h of like 1, 2 is equal to 3, right? Well, h of 3, 0 is also equal to 3, isn't it? There you go. That'll do it. I mean, that's all you really need to prove that it's not injective. So the answer here is no. It's not injective, and my proof is real quick and simple. I'm just going to write it like this. That's actually going to be the second line of my proof. I'm going to start by saying, consider these two domain elements, 1, 2, and 3, 0. Those are both elements of R cross R, which is our domain. They're not equal to each other. Let's point that out. Okay, it's pretty obvious, but just point out that they're not the same element. Yet h of 1, 2 equals 3, and h of 3, 0 equals 3. Oh, well, they give the same output, but they're not the same input. Therefore, h is not injective. All right, so notice that in order to prove surjectivity up here, in order to prove that it was surjective, we had to work with an arbitrary element. If we were trying to prove something is injective, again, you have to work with arbitrary elements, because injective is any time you have different inputs, you're going to have different outputs. So you can't use examples to prove that. But disproving injective can be done with a simple counterexample, a single counterexample, right? So similarly, you could disprove surjective by finding a single element in the codomain that doesn't have a preimage. Right? A single element that's not in the range. And that's because both surjective and injective are essentially defined using for all statements. They're defined with this something needs to be satisfied for all elements. And so disproving them can be done with counterexamples, but proving them has to be done more generally with arbitrary elements. So I just wanted to make that last point here. Now, I'm going to end this video by giving you an exercise. So let me pull out the example I did a few videos back. here we go. Just getting up my notes. Here we go. This example, we did this earlier. The x squared example and the x cubed example. So as an exercise, what I want you to do is figure out if these two functions are, like for each of them, figure out if it's surjective and figure out if it's injective, and then write a proof. Either prove or disprove each of those qualities for each of these functions. So we're going to prove or disprove surjective, injective for each function. Okay, give that a shot. That'll just give you some practice writing surjective and injective proofs, and it'll give you some practice, kind of grappling with the ideas and figuring out whether something's surjective or injective. And if you, once you finish that, what you can do is post your proof on the discussion board, and then we can have a little conversation about it. And I'll give feedback here and there as necessary.